One of the things I like about doing physics is that I enjoy being baffled. So I don't necessarily want to get through to the answer. And this again, Karl Popper said this beautifully in his passage in his autobiography about problems. He said, find a problem and fall in love with it and get married to it and live happily with it for the rest of your life till death do you part. And if by any chance you should happen to solve it, then don't worry, because there will be a host of enchanting problem children that will result from that. And I think that's exactly right. That's how I feel about physics.
Hello and welcome to the light side. I'm Anjali, a student in mathematical and theoretical physics here at Oxford, and I'm part of Wolfson College, which makes this conversation very special because my guest today is also a Wolfson Fellow. I'm joined by Professor David Deutsch, and I first encountered you through my lectures or my lecture notes when I was studying Introduction to Quantum Information Theory. Today, I'm very eager to talk to you more about the journey behind all those ideas. So let's start from the beginning. How was it growing up for you? And was there a special liking towards science or studying in general?
Yeah, I'm not sure exactly when I focused on physics in my childhood, but it was approximately when I began secondary school, like at 11 years old. Before that, I'd kind of vaguely thought I want to be a scientist, but my vision of what a scientist is was like shaped by seeing scientists on television with test tubes, and like it was more chemistry than physics that I had in mind, with white coats as well, and so more experimental than theoretical. But as soon as I found out what physics is, not only did I want to be a physicist, I wanted to be a theoretical physicist. So, you know, to know what the laws of nature are, and to find new ones, and to find out how the world is made up out of things that obey laws, that kind of thing. I did the usual O levels and A levels and stuff, particularly interested in those, but I wanted to do physics. So I had been told that the way to do that is to get into university and study physics, and then get a physics degree, and then do postdoctoral research and that kind of thing. So I headed towards that. Nobody told me that there are other ways of getting to the same place. Otherwise, I might have taken them, or I may or may not have been allowed to.
What are those other ways?
Well, the concept of a PhD, for example, is relatively recent. Newton didn't have one. So Faraday didn't have one. It was introduced in the 19th century. I'm not sure of the history, but and really introduced seriously in the 20th century. Just similarly, we today forget that peer review is a very recent process in post World War II, I think. So the setup that we have, which we think is so natural and inevitable nowadays, was not always so. And another thing I remember from somewhere is that, well, two things. One is that in Oxford, professors didn't lecture. The people who lectured were a lower rank of academic.
I
did
see.
the lecturing. And in Cambridge, it was not unknown for undergraduates to participate in scientific research. Not that there were many physicists in those days, but there were non-zero number, and the same in mathematics. So yeah, there were other ways, and there are other ways today, which are kind of suppressed by the what shall I call it, the career structure and the financing structure of physics research. And of course, there are far more physicists today than there were 100 years ago. But that has come along with the fact that happened because people came to think physics is important. And once they began to think physics is important, the government began to be involved. And once the government is involved, you have a natural channeling of financing and careers into the things that our government supported. But you asked what other means were there? Well, basically, you can start doing research in physics as soon as you get interested in physics. You can start doing that when you're 10 years old, if you're interested. And the physics you will do may not be that good, but if it isn't, and you remain interested, it will lead you into physics that is good. And some people do that.
Right. You mentioned how your interest sort of grew gradually as you studied physics in school, then go ahead in academia, do a PhD and all of that. So how did your perception of physics or science sort of change over time compared to when you were 11 years old and got interested, and how did it change over the years?
So it changed quite relatively suddenly. I mean, over a period of a couple of years, let's say. Starting, as I said, as soon as I realized I want to be a physicist or whatever you call it, that's already not a very good way of putting it. And it is not really what I wanted. But starting, let's say, 11 or 12 years old, until I got a degree, I regarded the educational system as a sort of vending machine. That is, I wanted something, namely the privilege of going on to do research in theoretical physics. And so my practice was to find out what is needed and then to do what is needed. I didn't have very much interest in it. I had quite a lot of interest in school physics, but I learned that long before school physics lessons. So, I would read the textbook in advance and then read next textbook and whatever. And so physics lessons were not exactly boring because you get a different perspective on a thing every time you hear about it, So I got different perspectives, and I liked having different perspectives on physics, but I also liked thinking about unsolved problems, whether the electron has a zero size or a non-zero size. I remember thinking about that to no avail, but still thinking about it was fun. And then the same when I was an undergraduate. I just found out that what you needed to do to get the requisite grades, and so then I did them. Then I applied to Department of Applied Mathematics and Theoretical Physics, as it's called, in Cambridge. Oh yeah, so I went to Cambridge, not Oxford. Sorry about that. And they just turned me down without even an interview. They said, before you do that, you've got to do part 3 maths. And I said, what's part 3 maths? It's the equivalent. It's a kind of MSc, but in mathematics. And if you want to do theoretical physics research in those days, you had to do well, not just do part 3, but do well in part 3. And I had taken a sacred oath never to do any more exams in my life. Immediately I had to renege on that oath because I had to do part 3. But once I got into the part 3 course, I realized that it was nothing like what I wanted. It was nothing like what I wanted to get on with some actual research. Now I had waited for so long to do so. So I did the absolute minimum necessary to just pass, not get a forgotten what they called the first class or A's or whatever you had in those days. But anyway, I no longer strived to do well in the exams. I didn't go to half the exams for a start. And the other half, I just did the bare minimum. I did a project. We were allowed to do a project, and that got very good marks. And I think that's why they, out of pity, let me pass. And but then I thought, well, I can't do research in damped Department of Applied Mathematics and Theoretical Physics because their attitude is completely different from what I want. And I had read Dennis Sciama's book about cosmology even when I was in school, and I read it again when I was an undergraduate. And saw that I'd missed most of what he was trying to say. But I definitely liked his attitude. And I saw that he had now moved to Oxford. Because he was in Cambridge before, but that was before I was appeared there. And so I wrote to him and said, I'd like to do research. I've read your book. I think it's great. But damped isn't for me. I've done part 3, but I'm not going to do well. I hadn't yet received my results, but I knew I was going to do very badly. I said, I'm going to do badly in part 3, but I'd like to come and work for you. So he wrote back. No emails in those days. So it was snail mail. He wrote back and said, yeah, come for an interview. So I came for an interview, and he took me as a graduate student.
So it was in cosmology, was it, that you started doing research?
No, because although Dennis Sciama was officially a cosmologist, and a lot of his work, not all, but a lot of his work had been in cosmology, initially in the steady state theory, and then in Big Bang theory. That wasn't all he was interested in. He was interested in fundamental physics. He was interested in exactly the same as what I'm interested in. I mean, that's probably why he accepted me as a grad student. So he had a research group called Theoretical Astrophysics, which was in a prefabricated hut outside the astrophysics building. No longer exists, but you can visit the place where it used to be. That was called Dennis's Hut. And he had, I don't know, a dozen or a bit more students there, and I became one of them. And and it was, I don't know whether it was sheer luck or whether it was because he thought about physics the same way as I do, that he didn't put any pressure on me or on any of us to do a particular thing. He was always ready with suggestions. If we said, what can I do next, or what should I do now, or what's interesting to look into, or what's the, so I thought at first I would do quantum gravity, because I thought, well, quantum gravity is the big unsolved thing, so I'll solve it. I soon realized that that's not on the cards, because it was obvious that we totally weren't ready to do quantum gravity. Like we didn't have the physical intuitions necessary to unify quantum theory and gravity. So I started trying to understand quantum field theory, and then this thing starts up of or started up where we were, of quantum field theory in curved space-time, that is, in a classical but curved space-time. And I think Dennis suggested, I can't remember, that I should join in with some of the postdocs who were studying quantum field theory, not in curved space-time, but in flat space-time with boundaries. And that then turned into my thesis. So I proved a few things, which I found quite fascinating, but I'm not sure they'd be considered fascinating today, about quantum fields in space-times with boundaries, which are approximated by quantum fields in things like waveguides, in things like surrounded by a conductor or something. So, but I was interested in what happens very near the conductor, which is not like real conductors, where things like conductivity and so on break down at very close distances. But an idealized conductor or an idealized boundary, with the different kind of boundary conditions one could impose, and so I filled up lots of. We used to work on the backs of computer line printer output, which was this wide, so I worked out some equations there, and that became most of my thesis. But meanwhile, halfway through my thesis work, I got interested in foundations of quantum theory, which then became quantum computing, theory. So that was how I got there, whatever there is. I didn't really know the difference between foundational stuff and not in my first year as a graduate student. Basically, what I had, if I can reconstruct now what I had in mind, is I thought the answer would be an equation. It would be like Einstein's equations, but with Q numbers, something like that. And the work that needed to be done was to make that meaningful. And I already knew there were tremendous problems even in non-gravity quantum field theory. But people thought, well, maybe if you add quantum theory, it'll make it easier rather than harder. So that's what I was kind of expecting, something like that. But as I just said, I soon found that the problems were really conceptual. And even if you found the right equation, you wouldn't know what it meant. You wouldn't recognize it as the answer, because the problem is conceptual. It's like if you got Einstein's equations but didn't realize that they were about curved space-time. You just have these complicated formula with additional terms, but what are they, and how can you tell the difference between one and another? So that Einstein couldn't have done it that way, and I think quantum gravity will not be done that way either. But meanwhile, I was on the one hand doing other things like the boundaries thing, and then I got interested in foundations of quantum theory, not necessarily gravity, and not even necessarily quantum field theory, but foundations of quantum theory, which should apply to both those.
Mm-hmm. So you talked a lot about unsolved questions and this attractiveness towards resolving what is not being done, what is not being known.
Yes.
So what are some questions today that excite you in the same way? What do you think would you do if you were going back to your undergrad or your DPhil days?
Well, so at the moment, I'm not even doing quantum computation. I'm doing constructor theory, which is an idea I had, which, if it goes super well, it'll solve all those problems, or it could completely fail and become less than a footnote in the history of theoretical physics. But I think it has the potential to solve a number of problems. Before I wrote even my first paper on constructor theory, I wrote a philosophical paper, which was basically why we need something like constructor theory. And I remember it had, don't ask me what they were now, but I remember it had like section 2 was something like motivations. And there were like 18 motivations from different branches of physics. So one of them is constructor theory is about both factual and counterfactual rules about what can be caused to happen and what cannot be caused to happen. And this is different from the conventional theoretical physics, which is about initial conditions and laws of motion. So the idea is to find the initial conditions, or to conjecture what they are, and to find the laws of motion, conjecture what they are, and then use those two things to work out observations and see if that fits the observations. That's the idea. One of the problems with that is that we have very little idea about the initial conditions. So forget about cosmological inflation. Without that, we just have a singularity at the Big Bang, and we don't know what the initial conditions at the singularity are. You can say, well, they should be homogeneous then. That's the simplest, homogeneous and isotropic at the Big Bang. Trouble is, it's not obvious what that means in a quantum gravity situation, because homogeneous and isotropic are kind of concepts from classical gravity. Second, if something starts off homogeneous and isotropic, it's going to end up homogeneous and isotropic. And we see that it isn't, at least on a small scale of a few billion light years. It's not homogeneous and isotropic. So it might be on larger scales, but you have to argue very hard to make that work. So then there's cosmological inflation, which is an idea for what happens if it's not homogeneous and isotropic at the very beginning, whatever that is. This inflation process is going to smooth it all out, and so that by the end of the inflation process at 10 to the minus whatever it is seconds, it's going to be very, very high. It's going to be reduced by a factor of 10 to the 60 or whatever it is. As Roger Penrose has pointed out, that's very unsatisfactory. At the level of 1 part in 10 to the 60 is still inhomogeneity. Where does that come from? Okay, so they say, well, it probably comes from quantum fluctuations, and they work out, quantum fluctuations and see what that would give. But again, it doesn't say anything about the initial conditions. It doesn't say whether before the era of inflation there was anything, whether there was a singularity, or whether there was an earlier universe, or whether something was governed by different laws then, or whether it was infinitely long before doing the inflation thing, and so on. None of that is known. There's no theory of it. It's just all hand waving. So in constructor theory, sorry, it's another long answer, but you did ask. So in constructor theory, things which actually happen are emergent consequences of things that could happen. The exact laws are about things that could or could not happen. And what actually happens is an emergent consequence of that. And so there are no initial conditions required in constructor theory. It's like, for example, if we say that such and such a thing is possible, such as building a universal computer, an arbitrarily accurate universal computer with arbitrarily large memory or whatever, if there was a law of constructor theory that said that, then that would imply something about the initial conditions, such as that they couldn't be homogeneous. So that would already tell us that something, saying this about what is possible and impossible, tells us at an emergent level what does happen or what did happen at the beginning of time. So I'm just hand waving here, as you can see, because we don't actually have a theory that says that, but we have a theory that could say that if we work it out properly.
Right. Walk me through it in a bit more detail then. Is it that the initial conditions don't matter in this case?
No, well, for what? So the initial conditions, the idea is the laws of physics do not state what the initial conditions of the universe are.
Mm-hmm.
Now, if you think that's odd, note that they also don't state what the conditions today are or what the conditions in the asymptotic future are. There are no such laws. We expect to work out such. If somebody asks, what is the asymptotic state of space-time, we don't expect to derive that from we don't expect that to be mandated by some fundamental theory, like it'll be homogeneous or whatever. We expect to work out an approximation to it, and that approximation, we hope, is accurate enough to answer the questions we want to answer about the distant future. Will we all be killed or not? And that kind of question. So in constructor theory, that is true of the initial conditions as well. We don't expect to have a law that says the initial conditions are so and so, but we do expect that that exact statements about what is or isn't possible today, or at finite times, will tell us approximately or at an emergent level what things were like near the beginning or at the beginning, just as they do in current physics about near the end or at the end.
Does most of your day look like thinking about this theory, working on it on pen and paper? Or what does a typical day look like for you?
Well, I try not to have typical days, but I'm working on several things apart from constructor theory or apart from fundamental constructor theory. Like and my books and my papers always take inordinately long to write. It's mostly that I have to churn what I say before what, and I spend like 90%, 99% of my time moving things. It's always moving them upwards, moving them earlier. But of course, you can't move everything earlier into the paragraph 1 of chapter 1. So it's a bit difficult. And eventually I have to work through all possible permutations of all the sections of all the chapters, which is exponentially hard, and that welcome to my world. So I'm writing a textbook together with Chiara Marletto and Sam Kuipers, which we hope will be the ultimate textbook, because it will use of textbook of quantum theory, of conventional quantum theory, not constructor theory, although its motivation is influenced by constructor theory. So it will introduce quantum theory via quantum information theory, quantum computation. That's one thing. It will introduce it not via the hydrogen atom and the harmonic oscillator. So that's one thing. And it will introduce it via the Heisenberg picture, not the Schrödinger picture first. And it will introduce it in terms of realism and discovering what the universe is really like, and not saying appalling nonsense like, if you think you understood quantum theory, you haven't. Which I don't know if any famous physicist really said that, but it's been attributed to several physicists, and it's certainly said a lot by people who want to shut students up. And that's not what we want to do. We want to do the opposite. Yeah, I've just finished writing a science fiction book about the Fermi paradox, and I'm writing a sequel or something. I don't know what to call it. A third volume in my the two semi-popular books that I've written. So about how rationality works. And then papers, I'm trying to write a paper about the universal constructor. Quite interesting, because the theory of computation kind of seriously begins when people realize that there's computational universality. I mean, Babbage, who made his difference engine, I'm not sure whether he knew at the time when he designed the difference engine that this was a special case of the analytical engine, which would have been a universal computer. Don't know if he realized, but he did eventually realize. But Turing realized immediately that the theory of computation is all about the properties of the universal, a universal computer, a universal Turing machine, or whatever. In constructor theory, it's not like that. The universal, although I think there can be a universal constructor, or approximations to it can be built in real life. I don't think that in any real sense, the theory, the constructor theory itself, is the theory of the universal constructor. I mean, it may yet turn out to be, but it doesn't look like it at the moment. So that's one thing I'm writing.
So quite a bit of interesting stuff. I see a lot of books on your bookshelf up there. Are most of those your books, or do you have some favorites that you keep going back to?
So this is a shelf of books that I very rarely read. So, for example, there's the Encyclopedia Britannica here, which I've almost never consulted since the emergence of Google. So that's a thing I would have used. There are some books that I use occasionally, just because I can't remember where I read so and so. But even that nowadays, the LLMs are getting good enough for me to say, where did I read about so and so, and then sometimes it tells me, sometimes it hallucinates. but if it tells me something, at least I can then look that up on Google, and then that may remind me. So yes, well, Macaulay is worth reading, and it's worth reading as a book, History of England. What else? I can never. People ask me what my favorite film is, and I can never. When I'm asked that, I can never remember any film. But I think I. Oh yes, so I like science fiction, or only certain science fiction. Neil Stephenson, Greg Egan, and then the old ones. Larry Niven and Arthur C. Clarke and Asimov and so on. So, do I still read those? I think they've lodged in my mind, so I don't have to read them. They're there in the library in my head.
Okay, I'm going to ask not a favorite movie, but do you have a favorite physicist?
So if you're asking who, in my opinion, is the best physicist, it's going to be either Newton or Einstein, and that's not a very difficult judgment to make. They're very similar in some ways, and they both revolutionized physics, and in more than one way, in lots of ways. And Newton was much more mathematical than Einstein. Einstein was much more intuitive physical than Newton, but it's a small difference with people at that level in the stratosphere. But I think the physicist that I admire most is Michael Faraday. I think he too thought of physics and chemistry in those days in the way I do. And now he's an example of someone who didn't take the usual path well, through a career. He was an apprentice bookbinder in a bookshop a few yards from the Royal Institution, and his boss had tickets to go to Royal Institution lectures, but didn't particularly want to go, so he gave them to Faraday. Faraday went to the lectures, got absolutely mesmerized by Humphrey Davy's lectures on chemistry. So he wrote up, he'd been taking notes for the lectures, he wrote up the notes in sort of very nice, and then bound it using his skill as a bookbinder, and then went to the Royal Institution and presented it to Humphrey Davy, and Humphrey Davy offered him a job as a research assistant. And within a few years, he replaced Davy in reputation, which Davy was not very pleased about. And then later, he replaced him as the head of the Royal Institution. And, then he revolutionized physics, not as much as Newton and Einstein, but still. So I like his style. I like the way that he approached problems. And I like all the quotes that I've heard from him, including the ones that he probably never said, but which are the kind of thing he said.
Which is that one?
For example, at one of the Royal Institution lectures, somebody said, yes, but what use is it? He'd been talking about electromagnetic induction, which he had discovered. And he's supposed to have replied, what use is a newborn child? So that's and another version of the story, or maybe he often said things like this. I think maybe that's more likely, that he was asked by a minister what use electricity would. This must have been a bit later, when he'd invented like electric motors and dynamos and whatever. He was asked by a government minister, what use is this going to be? And he replied, I don't know, sir, but I'm sure you'll find a way to tax it. So, this is my kind of physicist. He was interested in the thing. He wasn't interested in the applications of the thing, and he wasn't interested in the uses of the thing. Or rather, perhaps that's not quite the way of putting it. He was interested in those things, but that's not what he did research on. And that's not why he did the research. He did the research because he wanted to know how the world works, just as he had when he was an apprentice bookbinder, and thank heavens his boss gave him those tickets.
So true. I did not know of that story, and it's quite an interesting one.
Yeah, or two stories. I don't know.
Yeah.
It's possible that neither of them is true, but they are definitely the kind of thing he said.
When we think about these revolutions in physics, so there is a Newton coming up and changing the way we think about so many things, and same with Einstein. Do you think that today there are lesser unsolved questions? Do you feel like all the cool stuff has already been done in there?
Absolutely not. No. I think the problems at fundamental physics are more severe today than at any time in the past. We're lucky in that, for example, when in 1897, I think, Michelson made his very embarrassing statement during a lecture that we know what all the fundamental laws are, and physics in the future will be will be found in the 6th decimal place. And then within a couple of years of him saying that, the revolutions began. But Michelson can be forgiven, because in 1897, it really did look like, at least from a certain point of view, it looked like all the fundamental knowledge in physics was already known, and that all that was needed is to tidy up a few a few anomalies which will have an explanation within the existing way of looking at physics. I mean, I like to think that if I'd been around in 1897, I wouldn't have thought that, because I'm not interested in the sixth decimal place or in the first decimal place. I'm interested in how things work, and if an explanation doesn't quite match how things work, not just experimental things, but you know, Newton's theory has got instantaneous communication. If I shake an object here, everything in the universe moves according to Newton's laws. Newton knew this was a problem. He knew that he hadn't solved it. Then, you know, by 1897, people have kind of got used to that being an unsolved problem, but they didn't think it's serious. I would have thought it's serious. I hope, maybe not, but I hope that I would have thought it serious. So, you know, there's the big problem at present of the quantum gravity, or unifying quantum theory with gravity, or maybe that's not the right way to think about it. Maybe it won't be a unification. It'll be a thing that replaces both of them. That's you know, that's not going to be solved by a fudge. That's not going to be solved by making a small change in existing theory. That we know that that's going to require something conceptually new, and we have no idea what it is. Maybe it'll be constructor theory. I don't know. I mean, I'm not saying I have any idea of how that could happen, but I'm saying that in order to say we have no idea where it would come from, where this intuition or way of looking at the world would come from. It might come from some crank somewhere. So that's one. And then quantum field theory itself is full of fudges. And they don't tell us anything about what's going on underneath the mechanism of quantum field theory that works. Like, it works to give answers. It doesn't work at all to give explanations of why these answers are the right answer. So that's another thing that remains. Then there's the initial conditions of the universe. I probably can't bring to mind all of them, but I mean, if I had half an hour to write a list, I think I could write a list of about a dozen really fundamental things that obviously are going to require new conceptions, and where it's obvious now that is so, but it was not at all obvious in 1897. So we're lucky, as I said.
Mm-hmm. Give me, say, top 3 on that list.
The quantum gravity, foundations of quantum field theory, and initial conditions of the universe. Those are 3. But if you want another one, see if I can say some more. Well, so there's the foundations of thermodynamics, which Chiara Marletto has made fantastic progress in understanding those via constructor theory. And I think that project, if I had to guess, which I shouldn't prophesy the future growth of knowledge, but it seems to me that is the route to the foundations of thermodynamics, which will explain, for example, why there is such a thing as black hole entropy, what happens to information in a black hole or in an exploding black hole or an evaporating black hole. That I think constructor theoretic thermodynamics, I guess, is going to be the path. It's not going to solve those, but it's going to be the path to solving those, I guess.
So these are areas to look out on.
Yeah, I think my colleague Vlatko Vedral has just written a book called something like Portals to a New Reality. I haven't read it yet, but I understand from the blurb that it's about what in this conversation we've been calling problems at the foundations of physics, where the portals he talks about are routes towards understanding those things. Like, for example, his work with Chiara about how you would test, how you would get what they call what do they call it? Not testimony, but something like testimony, a witness, that's it. How you get a witness to the quantum nature of gravity. So it's often said, always said in textbooks, that since we can't measure anything at the quantum gravity level, the world is exactly the same as it would be if gravity was not quantized. But that's a very silly thing to say. And their thought experiments, which might even become real experiments, are ways of contradicting that bad idea.
Mm-hmm. So I also want to ask if there are young researchers today or people who are just curious about doing physics and doing theoretical physics, what advice do you have for them?
Well, I try never to give advice because for many reasons. One of them is that if you give advice, then if it goes wrong, it will be your fault. But a more principled reason is that you can't really know what direction is best for another person. And if I could say a meaningless thing like do the thing which you like best, but that really doesn't tell you what to do. And there's also the fact that giving advice is a bad relationship. And I would, it's an asymmetrical relationship. And in as Karl Popper said, in our infinite ignorance, we are all equal. So I don't want to set my infinite ignorance up as being less than somebody else's. So I would say this. If you're interested in something, then you can pursue it, even if you are also pursuing something else. If you're put off by the riskiness of it, then note that the conventional path is also risky. It's not guaranteed. But by the way, Dennis Sciama said this to me at my interview with him when I was applying to be a graduate student. A PhD does not guarantee you a job in physics. And if you get a job in physics, it may not be an aspect of physics that interests you. So why not just go for the aspect that interests you from day one or from day minus 1,000? Just do it. Sorry, that is a sentence in the imperative mood. And I don't want to say anything imperative. So I should say, consider just doing it. Why not just do it?
Amazing. So we often touched upon the fact that theoretical physics is about understanding how the universe works and how nature works, and trying to figure out a theory or trying to figure out an equation, say, which could tell us more about that. But I'm a theoretical physics student, and I get this very often, that why should anyone care about theoretical physics if in their normal lives, if they don't study theoretical physics? So my question to you is, should regular people care about theoretical physics?
So I think that question is the same as, should everybody care about theoretical physics? Because there'll be the regular people and the irregular people, and that includes all people. No, I don't think there's any should about it. It's people who have a desire to know how the universe, to learn. And yes, I should have said earlier that one of the things I like about doing physics is that I enjoy being baffled. So I don't necessarily want to get through to the answer. And this again, Karl Popper said this beautifully in his passage in his autobiography about problems. He said what you should do, and as a philosopher, but it applies equally to a physicist or to any scientist. Find a problem and fall in love with it and get married to it and live happily with it for the rest of your life till death do you part. And if by any chance you should happen to solve it, and I like the way that he regards this solving it as a bit of a downer, you know, that's kind of, so then he said, if by any chance you should happen to solve it, then don't worry, because there will be a host of enchanting problem children that will result from that. And I think that's exactly right. That's how I feel about physics. You also spoke about revolutions in physics. I don't think that Newton or Einstein or Faraday, the three we've mentioned in this chat, I don't think any of them wanted to revolutionize physics. All of them wanted to know what's out there, how it works, how it behaves, why it behaves the way it does. That's the kind of thing they were interested in. It so happens that they discovered those things, and that those things then had all sorts of side effects and so on. But I think the reason they wanted to think about it is that they were interested. They liked being baffled by these things that they discovered along the way there. I like being baffled to the extent that I sometimes get into the mindset of being a bit reluctant to pursue something in case it gives the answer. I have to stop myself thinking that.
I think that's a wonderful thought to end this conversation at. All right. Thank you so much for your time. Thank you so much for being here and for sharing your wonderful thoughts. It was an absolute pleasure, an absolute honor.
Nice to meet you too. Okay. Bye-bye.
Bye.
Nice chatting.